Okay, so we were dealing with these identities that we proposed, right? And the first two we have already proved. Now we have to prove the third one. Okay. Since E minus F is a subset of E, we have D minus E a subset of D minus E minus F. Why though? You see, you can prove it also logically, but you can think in terms of Venn diagram. This is, say, E minus F, and this is E. E minus F is a subset of E. Now suppose you have D like this. Now what is D minus E minus F? That is this one. You have to avoid E minus F. But what is D minus E? D minus E is this much. So you can see that D minus E is a subset of D minus E minus F. So, or in another sense, if you want to understand why it's like this, E minus F is smaller than E. So when we are subtracting E, we are actually subtracting more from D than when we are subtracting E minus F from D. So that's why D minus E becomes smaller or is contained in D minus E minus F. Okay. So this is a subset of this. Now we come to this. Next, D intersection E intersection F is a subset of E intersection F, no doubt, because it's an intersection of D and D intersection F, and E intersection F is disjoint with E minus F. This also we already know. Hence, D intersection E intersection F is also disjoint with E minus F, because there is no element common between this one and this one, and this set sits inside this one, so definitely there will be nothing common between this one and this one, and that's what we have written. Since we also have D intersection E intersection F, a subset of D, we conclude that this intersection is a it's better to use brackets, no? It looks neat, that this intersection is contained in D minus E minus F. Now what is happening here? You see, suppose you have, this is D, this is E minus F. Now D minus E, this intersection is a subset of D, so it will be inside D, but at the same time it has no element common with this one. So that means this set will avoid this area, because here elements of E minus F are there. So that's why this is a subset of D minus E minus F. This part is D minus E minus F. Okay. So now we have got two things. One is that D minus E is a subset of this set. At the same time, this intersection is also a subset of this set. So the union of this set and this set will also be a subset of this set. Hence, we have D minus E union D intersection E intersection F, a subset of D minus E minus F. So we have got one part of this equality, one containment. We will now prove the next one. I mean the other one. Next, let X be any element. We will now have to prove that this is a subset of this. X be any element in D minus E minus F. Then X is in D and X is not in E minus F. Now two cases arise. Under this condition, X may either be an element in E or not an element in E. If X does not belong to E, then since X belongs to D, this implies X belongs to D minus E. Okay, this is very easy. On the other hand, if X belongs to E, then what happens? That we have to now see. Now assume X belongs to E. Now look at this. See, this is E, this is F. This much is E minus F. X is in E, okay, but X is not here. So that means X has to be in E intersection F, because there is no other place for X to go. Since, so we can write it like this, since X does not belong to E minus F, we must have E intersection F. But also X belongs to D, and because X belongs to D is always there, whether X is in E or not in E, X is always in D according to our hypothesis, and hence X belongs to D intersection E intersection F. So in any case, X is either in D minus E or in this intersection. It is in D minus E when it is not in E, and it is in the intersection when it is in E. So that means X will be in the union of these two sets. Therefore, X belongs to D minus E union D intersection E intersection F. And this proves that any element here is also here, so that means this is a subset of this. Hence D minus E minus F is also a subset of D minus E union the intersection of these three sets. And combining this with the previous inclusion. Previous inclusion means this one, you understand what I am talking about. Previous inclusion, we have equality. This last one looks extremely counterintuitive. I mean, we just looking it at once, we cannot understand why it looks like this, but it will prove helpful in what we are going to do now. Since we will need these three things, we will keep them here. Okay, now with the help of these three identities, we are going to prove our actual claim about A plus B plus C. So let us recall that claim and start proving that claim. We now prove the claim that A plus B plus C equals A minus B union C union B minus A union C union C minus A union B union the intersection of the three sets. This is what we want to prove using these three identities. In doing so, we will make use of the identities 1, 2 and 3 without explicitly mentioning them. I mean, at some stage, at some steps, we have to use the third identity. We will not write it explicitly alongside the step that this is being used. I will say what I am using at the time of using that, but we will not mention it in the solution. It will be evident. Okay, and these are not the only things we will be using. We may have to use the already known set theoretic identities like distributive laws and such things. Now, to prove this claim, we don't have to start by considering elements in the set. Because of the availability of these identities, we can now directly start from this itself. So we have a plus b plus c. First, let us write the meaning of this plus, the outer plus. It's the symmetric difference of a plus b and c union c minus a plus b. We will need many brackets, but I will refrain from using curly brackets because curly brackets denote sets, right? So that may create unnecessary confusion. Now we write the meaning of a plus b. So it is the symmetric difference of a and b. Minus c union c minus a minus b union b minus a. Okay. So now in the next step we will use this one. See, D union E minus F. We have something union something minus C. So in its place we can write A minus B minus C union B minus A minus C. Ideally I should put this inside brackets, but since we have union and outside also we have union, so we can get rid of that bracket. Union. Now I have to write this one. Here however this part will be used. See, D minus E union F is equal to, it's like the De Morgan like law. Union. So here I have to use bracket because this union is going to be intersection. C minus A minus B. Note carefully how we are using these identities and what we are using at each step. So C minus A minus B intersection C minus B minus A. Here we have intersection, so we have to use brackets. Okay. Now for this one we use the first one again. In place of A minus B minus C, I can write A minus B union C. And you can see that whatever we are claiming, part of that is coming. Just like that, union B minus A union C. Union. Okay, now this is the place where we have to use this third complicated counterintuitive one. So let us do that. C minus A minus B means C minus A union C intersection A intersection B. Okay. Intersection, then this one C minus B union C intersection B intersection A. Right. A minus B union C union B minus A union C union. Okay, now let me write one more step so that just for the sake of more clarity. C minus A union, instead of this I can write A intersection B intersection C, because intersection is associative, commutative. We already have proved those things. intersection C minus B. Now here also we actually have the same set. Union. Okay, now in place of this whole complicated thing, I am going to write C minus A intersection C minus B union A intersection B intersection C. The question is, what have I done here? You see, this is nothing but distributive law, one of the distributive laws. Union distributes itself over intersection. So this normally what we do, we have something like this, we apply the distributive law and we get this, but here it's in the opposite order. So you have C minus A union A intersection B intersection C intersection C minus B union A intersection B intersection C. So we have used the distributive law here. Okay, now union, I have to write from there. Now what is this? This one is, again we can use part 1, I mean identity 1 here, the second part of the first identity. So this becomes equal to, oh sorry, I am not done yet here, union C minus A union B. We have used this one here. Where? Here. Union A intersection B intersection C. Now since the outermost operations are unions, all unions, so I can get rid of the bracket here, these two brackets. And see, this is what we had to prove. This was our claim. So this establishes the claim. Now with the help of this claim, we are finally going to prove that addition is associative. Okay. Now we start with A plus B plus C. In place of that, we can write B plus C plus A. Why? It seems that we have used the fact that this addition is commutative. Is it the case? Let us see quickly. According to the definition of addition, it is A minus B union B minus A. Since union is commutative, I can write B minus A union A minus B. So, and that is nothing but B plus A. So the addition operation we have here in this exercise is actually commutative, although it has not been mentioned anywhere in the exercise, but it's the case, and that's what we have used here. Now we apply our claim here in this, for this formation of sets B, C and A. So it will be B minus C union A union C minus B union A union A minus B union C union B intersection C intersection A, and this can be rewritten like this: A minus B union C, because all are the outermost operations are union, and union is associative and commutative. Then union B minus A union C union C minus A union B union A intersection B intersection C. Intersection is also commutative and associative, and this again according to our claim is nothing but A plus B plus C. So that's how we have, after all these things, we have the fact that addition is commutative. It is somewhat long, but that's just the way it is. So and this is only part A. Okay, we have still the other parts to prove. So next we move on to part B, which is a distributive law. Distributive law means just this one: A dot B plus C is equal to A dot B plus A dot C. We have to prove this. Let me just do it from there. We don't need these identities anymore. They have been devised solely for the purpose of using in part A. Okay, so in part B, we start with the right hand side. We have A dot B plus A dot C. This is equal to, dot means our multiplication is nothing but intersection plus A intersection C. Then we apply the definition of addition. A intersection B minus A intersection C union A intersection C minus A intersection B. Okay, now it seems we do need those identities anyway. So this becomes A intersection B. So keep in mind that these are De Morgan-like. If you have union or intersection in a set which is being subtracted from some other set, you just think of De Morgan's law. That's it. Here we have intersection, it will become union. A intersection B minus A union A intersection B minus C union. Since we again have union, so there is no need to write another set of brackets. Like that, here A intersection C minus A union. Here also this intersection will become union A intersection C minus B. Okay. Now A intersection B is a subset of A. So that means if we remove A from this, nothing is left. So that's why this is the empty set, because there cannot be an element in A intersection B that is not in A. Every element in A intersection B must be in A, because that's why it's a subset of A. So there is nothing in this difference, so it's empty. Union. Now in place of this, I am going to write A intersection B minus C I will say why this is justified. Let me first write the things. Union, again just like this one, if I subtract A from A intersection C, since this is a subset of A, I am going to get the empty set. Union, again in place of this I will write A intersection C minus B. Now the confusion is in these parts, right? Let us just quickly see. It's not very difficult. You take an element in this set. This happens because we have AND throughout. X belongs to A intersection B minus C. This implies X belongs to A intersection B and X does not belong to C, right? This again, this means X belongs to A and X belongs to B and X does not belong to C. Since we have AND throughout, instead of these brackets you can write like this also. So this will become, if I write from here, X belongs to A and X belongs to B and does not belong to C. That means X belongs to B minus C. So this implies X belongs to A intersection B minus C. So if you have A intersection B minus C, in its place you can write, you can write the bracket in any way you want. You can write A and B together with intersection in between them, or you can write B and C together with difference between them. It looks quite risky, but it happens because we have AND throughout. And the other way also you can come back, so they are actually equal. So that's how we get this is equal to this and this is equal to this. So finally what do we have? A intersection B minus C union, outside we throughout have union, A intersection C minus B. So now we are in a position to use one of the distributive laws, namely the one which says that intersection distributes over union. So in its place we can write A intersection B minus C union C minus B. So here we have used the distributive law. Now this is again B plus C. So this is A intersection B plus C, and since intersection means multiplication for us, so we get A dot B plus C. So that's how we have the distributive law. Okay, what about C? C asks us to show that A dot A is equal to A. This is almost trivial. Nevertheless, we have to write the solution. That's it. D. A plus A equals the empty set. By definition, this is A minus A union A minus A. That's it. And then E. E is a cancellation law. It is given that if A plus B equals A plus C, then B has to be equal to C. Okay, so assume A plus B is equal to A plus C. Then by parts A, that means where we have proved that addition is associative, part A and part we have written parts A and D. We have